Okie doke. So, before we continue on talking about thermodynamics today, which I'm sure everybody is really excited about, I know I am, I wanted to just point out this interesting article that Professor Castellanos sent me earlier. We're getting a little bit ahead of ourselves because we haven't really talked about carbon capture or anything like that. But the short version here is that there are various ways of removing CO2 from the atmosphere. One of them is to capture it at the point of generation. So like putting an amine scrubber on a coal power plant, that's fairly common. The other way of doing it is through a technology called direct air capture, which is where you actually just cycle ambient air through this machine that pulls out the CO2. There's a lot of engineering challenges associated with that we'll talk about in a couple of weeks. But it's a big part, it's expected to be a big part of a lot of these net zero by 2050 targets. So there was a company called Carbon Capture Inc., which that's a really clever name, that they were going to build one of these large direct air capture facilities in Wyoming. And one of the problems with direct air capture is that it's very energy intensive, because of the way it works. And so they were proposing to build this facility in Wyoming and use renewable energy for the power that's needed for it. But they just announced, this is 2 days ago, that they are pausing this project development. And the reason is that high competition for renewable energy from rapidly growing data centers. Okay, so this is kind of an interesting twist here in, net zero meets AI. Okay, think about all the computing power that's required for a lot of this artificial intelligence and all the other things that we use with these computing centers. There is only a certain amount of electricity that is being generated today, and obviously people are working to increase that amount, but there are significant bottlenecks. And here's an instance where computing centers are winning out over carbon removal. So it's kind of an interesting point. Anyway, I'll probably drop a link on Canvas to this story if you want to read more about it. There's some interesting things in there. Okay, but anyway, back to our piston. Okay, so just to recap, there's a question back there. Yes. It depends. The answer is there can be, but it depends a lot on a lot of the details of how the electricity is being generated from what non-renewable source. So yeah, I think in the extreme case where you're running, and it's kind of like what we were talking about with electric vehicles, right? If you're running off of 100% coal generation, then no, you're not going to come out ahead. If you're running off of a typical mix like what you have in the US, then yes, you will come out ahead. But obviously, the most ahead that you can come out is with 100% renewable. And the reason that this company was planning to do, or one of the reasons that this company is planning to do that, is because there are significant tax incentives in the 45Q tax credits in the Inflation Reduction Act for carbon capture using 100% renewable. That's like the most tax rebates you can get is by that technique. So that, from a financial standpoint, that's why they were doing that. Okay, so we were talking about entropy, and I'm just not happy with how this microphone is. Okay, that's better. So we were talking about entropy last week, and as we know, entropy is a measure of the amount of disorder in the system. Higher entropy means higher disorder, and we know that it's calculated from this formula from Boltzmann, where omega is the possible number of configurations the system can have. Remember, I talked about you all sitting in your chairs and then people in the classroom next door sitting in their chairs. The second law of thermodynamics says that you can only change the energy state of a system if the entropy increases. Okay, so we are going to talk about path dependence versus path independence. Okay, what the heck does that mean? Well, I will explain this a little bit. So we're going to talk about a system that's changing state. And when I say state, I don't mean driving to Louisiana. I mean, you're at a specific temperature, pressure, and composition. So those are the three variables that we're talking about. We often refer to that as PTX, pressure, temperature, and composition. And we're going from one state to another. So you can either change the pressure, or the temperature, or the composition, or some combination of those three. If the process is reversible, what that means is that we are not deviating that much from thermodynamic equilibrium, and that implies that it is a nearly isothermal process. Okay, so if we are transferring heat to or from the system, there's going to be a change in entropy because, again, remember, we're changing the state of the system. And we calculate that change in entropy, we're going to call it delta S. It is simply the amount of heat transferred divided by the temperature of the system. And you can think of that as an integral between whatever your first state was and whatever your second state was, where you're integrating the change in heat, or the amount of heat being transferred as you move between those two states. Okay, so we're using this lowercase delta here to explain that the heat transfer does depend on the path you take in pressure, temperature, or composition space. And I'll explain this on the next figure. But the change in entropy is independent of the path you take in that space. So here's what that means. So don't worry about this here on the left right now, but let's imagine that we are changing states simply in pressure volume space here. So you're going from state A to state B. And there's an infinite number of ways you can do that in pressure volume space. You could take path 1, which looks like that. You could take path 2 that looks like that. You could take any number of paths through that space. And if you're an isothermal process, the heat transfer is simply going to be equal to the pressure volume. Remember, we derived that on Friday from the first law of thermodynamics. And you get that work by integrating between V1 and V2 over the path you take in PV space. Okay, and where you get the path dependence is because remember that when you're integrating, you're just calculating the area under the curve, right? So the area under path 1 is going to be larger than the area under path 2. That's explained very nicely in this figure over here. So to travel on path 1 is going to take more work than traveling on path 2. So that is a path-dependent process. But overall, the change in entropy is going to be the same because it really just depends on the difference in the two end states, right? You have a certain number of configurations that the system can attain at point A, and you have a different number at point B. But that doesn't depend on how you get from point A to point B. That is a path-independent process. So entropy doesn't care what path you take, but the work does. So you can expend different amounts of work changing states for the same change in entropy. Okay, so that's what that means. So let's do an illustrative example with the piston that we talked about earlier. So we talked about doing work on the piston doing work on its surroundings by trying to take up the space of the stuff that's around it. So let's imagine that we've initially got this piston with some kind of gas in it, and it's at 10 atmospheres of pressure and a temperature of 298 Kelvin, so about roughly room temperature. Now, if we do an isothermal expansion here where we reduce the pressure to 1 atmosphere, so this is our end state, 1 atmosphere, 298 Kelvin, how much work can be extracted from that gas expansion? Okay, so we're going to go back to first law of thermodynamics. So the change in energy is going to be the sum of the change in internal, potential, and kinetic energy. And that's going to be balanced by the heat transferred to or from the system, and then the shaft work and the PV work being done by the system. And remember, these are negative signs because the system is doing the work on its surroundings, right? It is expanding, it's pushing stuff out of the way. Okay, now because we're isothermal, delta U is 0. We'll assume the system is at rest, so the kinetic change in kinetic energy is 0. Let's assume that we're not changing our position in any kind of potential field either, so change in potential energy is 0. So that means that the sum of these terms over here has to be equal to 0. And so that means that the heat transfer is going to be, we'll call that reversible heat transfer, and that's going to be equal to a reversible work term, which is just the sum of the shaft and the PV work, okay? Now, the work being done here, it's due to the expansion of the gas. And so remember, as we talked about before, the heat transfer, you get that by integrating along the path between the two states. So these are two different states here. The composition is the same, the temperature is the same, but the pressure is different. So again, remember your PTX, we're changing the pressure in this case. So these are two different states here. And the change in entropy is just going to be the reversible work divided by the temperature, and we can substitute that into our integral here. So if we have an expression for pressure and temperature as a function of volume or some way to relate those three things, we can actually come up with an analytic expression for this integral, okay? And so that type of relationship that links pressure, temperature, and molar volume of a material is called an equation of state. And the easiest one that we've all learned is the ideal gas law. That is an equation of state, PV equals nRT. And so we can solve this for the pressure like this. And now we can substitute that in here into our integral. And so this is what we get for the change in entropy. So I've substituted ideal gas law in here. And then the temperature cancels out. So now it's just in terms of molar volume. And so the change in entropy is just given by the molar volume at the beginning and at the end. And so again, you can see there's no path dependence here in the entropy. All I care about is what are my end state molar volumes. That's the only thing that matters here. Okay, and so now we can make a substitution for volume instead in terms of pressure using Boyle's law. And now we can see that the change in entropy is done by just plugging in all the numbers we get. And so we are getting a change in entropy of 382 joules per Kelvin, or 91.5 calories per Kelvin. So that's how you express entropy. It has units of energy per temperature. So that's kind of an interesting way of thinking about it. So that is the change in entropy between these two end states. And again, you can see that the delta S is positive. So we have increased the entropy of the gas here. Okay, and we can now calculate the reversible work that's being done by the same process. Inserting the ideal gas law, we don't have the temperature over here on the right. So now we need to know the absolute temperature. But knowing that, we can see that the reversible work that was done in this case was 114 kilojoules. So that is the total amount of work that we can expect this expanding piston to do on its surroundings. Now we can also separate out what's the pressure volume work that's done. And that is just integrating, again, the pressure with respect to molar volume. And because the final pressure is a constant, that just gives us this. And we can substitute the ideal gas law, so everything is in terms of pressure. And we see that the pressure volume work was 44.6 kilojoules. So that is work that you can't use for anything useful because it's the work of the gas just pushing stuff out of the way. So the total reversible work was 114 kilojoules. The PV work was 44.6 kilojoules. And so the usable work, the shaft work that we can actually get from this process It's just the difference between those. So it's 69.4 kilojoules. And that would be, say, if you compress that gas and then you let it expand, like in an internal combustion engine, that is the maximum amount of energy that you can get from that expansion. Again, this assumes 100% efficiency and all that good stuff. Okay, so the takeaway points of this little exercise here about thermodynamics and entropy is that so first of all, we assumed everything was reversible. It's generally not going to be reversible because of losses to friction and that sort of thing. And so that means that we'll probably get less energy out of the system than we would calculate. The ideal gas law dictated the path that we took in pressure volume space. You could do any arbitrary path. The math just gets more complicated in that case, but it's easier to do. But the end result won't be different in terms of entropy, okay? And the other thing is that we started off with a compressed gas, and you have to compress the gas somewhere to begin with. And that requires energy from some kind of an external source. So you have to put the energy in to be able to extract it at the end of the day. It's not a perpetual motion machine, right? And so the places that we get that energy from can be a number of different things, but the main things we are concerned about here is going to be energy that produces heat, mechanical work, and or electricity. And those are really the things that we use in our everyday lives in terms of energy. We use electricity for a lot of stuff, right? We use mechanical work. That's important. Like if you go take the elevator, that is energy being used for mechanical work. And then heat is another thing. A lot of the time we are producing waste heat, but in the winter when it's cold, you might use energy to actually produce heat. And I guess if you're running the air conditioner, that's kind of the opposite of heat. So it's a backwards heat pump. But these are the things that energy is producing. So just remember, anytime we're talking about sustainable energy, we're using it for these end uses. And it's not just electricity, it's not just heat, it's all of these things combined that are useful. Okay, I want to close with this slide that I showed earlier. So there's a lot of discussion about what is the mixture of energy sources going to look like in the future as the energy transition progresses and we make the transition to lower carbon forms of fuel, decarbonizing electricity production, that sort of thing. There's a lot of different organizations out there that make these forecasts about what they think the energy mix is going to look like. There's the couple that I like to look at are the Energy Information Administration, which is part of the US government that aggregates energy statistics and makes forecasts and reports and that sort of thing. Every year in about November, they put out their International Energy Outlook. So the data I'm showing you here are from last year. Hopefully over the course of the semester, we'll get the next installment. But what you can see is looking at the numbers from 2022, primary energy use around the world was dominated by fossil fuels. You can see that renewables are up here at the very top, accounting for less than a quarter of worldwide energy production. They run a whole bunch of different scenarios here, mainly based on prices of materials and commodities. So you can see, they're considering the cost of zero carbon technology, economic growth, different oil price cases. You can see that in all of these scenarios that they run, they are still predicting that by 2050, we will still be producing a significant amount of our energy from fossil fuels, anywhere from about 2/3 to maybe 3/4. Okay, so that's not a whole lot different from what we're using today. And so if you think about, if you want to get to net zero by 2050, you've got a lot of CO2 emissions from fossil fuel that need to be abated somehow. So we talk about carbon capture, carbon removal, those sorts of things. Those are going to be very important technologies in the future. The other source that I like to use is the BP energy outlook. BP, for some reason, has taken it upon themselves to do these big forecasts every year of energy use across all sectors. They caused a little bit of a stir with their most recent energy outlook because they are predicting that, well, they're predicting a number of different things, but they're predicting even in their business as usual scenario, which is this current trajectory. So that's if we just keep doing the things we're doing with energy into the future. We will see a maximum in primary energy demand sometime in the 2040s with a reduction thereafter. And if we go towards net zero by 2050, there's going to be an even more rapid decline in primary energy. The thing that really caused a stir that I'm not showing here, but was that they were forecasting a peak in demand for oil within the next decade or so. And that was kind of a significant thing for a large oil company like BP to be making that claim. But you know, that's what they see as what's coming in the future. But if you look at what they forecast by 2050 for by energy type, even in their net zero scenario, you can see that we're going to be getting maybe a third to a quarter of our energy from fossil fuels. So again, the carbon emissions, you're going to need to do something about that, and we'll spend some time talking about what that is. But it's interesting to ponder. Okay. So that's the end of that unit. Maybe I'll pause here and see if there are any questions. Tommy, how long has BP been doing this? As long as I can remember. I think, I don't want to speak out of turn. I think at least back through the 1990s, but I could be wrong. Yeah, that's a good question. I'd be really interested in seeing a hindcast about how good their predictions are. I don't know. Yeah. So what is this peak attributable to? Increases in efficiency. So everybody's using LED light bulbs. I know I talked about this the other day, you know, things like that. Even if we just keep the same energy mix in 2050 that we have now, you know, things will be run more efficiently and will require less energy. Okay. I'm just going to give you a little preview of what we'll talk about on Friday, which is going to be, we're going to talk about the energy transition and what that really means. I know that some people like to say energy expansion, some people like to say energy transition. I think transition is a more appropriate term. But I'll close by showing you guys this figure here. So this is looking at primary energy consumption in the United States going back to 1950. And you can see that since 1950, the dominant source of energy, and remember, this is not just electricity generation, but this is all uses of energy, has been petroleum, so oil. Natural gas has really taken over recently. But I think the biggest story over the past 20 years or so is what's happened to coal. It's really come down. And if you think about the growth in renewable energy, when you compare it to the total energy consumption, it's still minuscule. So this is an interesting thing to ponder about how that might change in the future. Okay, I will stop there for today. Thank you all for coming, and I will see you all on Friday.